Hello, my name is Hongwon Wu. I'm a master's student at Sohon University and currently a visiting scholar at Carnegie Mellon University. Today, I will talk about our work, relational self-supervised distillation with compact descriptors for image copy detection. Image copy detection, or ICD, is the task of identifying edited copies of images within an existing database. This is widely used in online sharing platforms and social networks to filter content for copyright protection. ICD addresses a more complex challenge by focusing on detecting exact copies of the images themselves, rather than identifying representative objects. It deals with precise duplicates of images that undergo severe transformations, such as re-encoding, merging, cropping, or color distortion. To better address these challenges, recent studies have leveraged self-supervised learning methods to directly apply data augmentation as their training objective. Despite advancements, a critical question arises regarding how to achieve strong performance with lightweight networks. It is known that lightweight networks, due to their limited representation power, struggle to directly leverage SSL to produce acceptable performance. While dimensionality reduction methods such as PCA can be used to create small-sized descriptors, they often result in significant performance degradation. Additionally, dimensional collapse, a common issue in contrast to learning, has been identified as a major cause of performance loss in previous works. However, our approach focuses on addressing dimensional collapse specifically for compact descriptors. Knowledge distillation is easily used by attaching to an existing task objective. In classification tasks, this is achieved using cross-entropy loss to distill label supervision. However, for unsupervised tasks like image copy detection, where labels are unavailable, alternative distillation approaches are necessary. Existing SSL-KD methods aim to enhance the representation ability of the student network as a pre-training method. Some researchers use relational information among instances. An instance-by-instance similarity matrix is used to distill the teacher's knowledge into students. However, these methods lack the ability to produce robust transformation variant descriptors required for specific tasks by ICD. Our aim of this research is to answer three following questions. First, how can we make a small network with small sizes descriptors? Second, how can we ensure that compact descriptors exhibit a uniform distribution of features while mitigating dimensional collapse? And lastly, how can SSL with KD be leveraged to produce compact transformation variant descriptors for the ICD task? Now I'll move on to our method. First, we have the teacher instance queue. The teacher network keeps an instance queue that stores embeddings of various instances. When a new input comes in, the teacher calculates similarity scores between the input and the embeddings in this queue. Next, we move to relational knowledge transfer. The idea here is to help the student network learn their relational structure from the teacher. To do this, the student aligns the similarity distribution with the teachers within KL divergence. By aligning the similarity distribution in this way, we ensure that the student captures the relationships between instances encoded in the teacher's feature space. Essentially, this approach allows the student to replicate the teacher's relational understanding effectively. In RDCD, the student network is trained using three different objectives. Our framework integrates relational self-supervised distillation, contrasting learning, and hard negative loss. First, we use a relational loss, which ensures that the relational structure of the embeddings in the student's space matches that of the teacher. For this, we calculate similarity distributions for both the teacher and the student. These distributions are computed using cosine similarity across the embeddings in their queues. Next is the contrastive loss. The student network generates descriptors for two augmented views. Descriptors are projected to a lower dimensional space, contrast learning. Finally, the descriptors from the momentum student are stored in the student's queue, which is used to compute the contrastive loss efficiently. Lastly, we have the hard negative loss. In the copy detection scenario, the primary challenge for Training arises from the hard negative pairs and the fact that the use of small descriptors renders the environment susceptible to dimensional collapse. To address this, we employ the hard negative loss to finally control the entropy and minimize the hard negative pairs. Three tables present the results from the DIS 2021 and copy days 10K and DC dataset. For each table, the first section summarizes the performance of different methods with varying descriptor sizes, while the second section presents the performance of our baseline SSCD strategy using a lightweight network with a descriptor size of 64, 128, and 256. The third section shows the results of the proposed RDCD approach. When compared with the methods outlined in the first section, our method achieves competitive performance despite using significantly smaller descriptors and a more compact network size. The visualization on the right shows how our approach maintains high performance while using significantly smaller descriptor dimensions. We conduct a ablation study where we analyze the effectiveness of each loss term and the interplay between them. In the first section of the table, we explore the contribution of each loss term. When only contrast-based loss is applied, the performance is limited, but adding a relational loss improves the micro-AP significantly. And finally, with the addition of hard negative loss, the model achieves the best performance with a 65.8 performance at descriptor size of 256. Also, we calculate the new metric ratio of preserved representation, which indicates the proportion of descriptor dimensions that avoid collapse. By appropriately balancing hard negative loss and relational loss, we ensure that all dimensions are effectively utilized. And finally, we tested the effect of using a different teacher model, Dino. We discussed three key points of RDCD: effect of RSD with hard negative loss, effect of hard negative loss on uniformity, and practicality of RDCD. First, I'll talk about the effect of RSD with hard negative loss. We focused on two key aspects: resolving dimensional collapse and the ablation of hard negative loss. By combining RSD with hard negative loss, we achieve a full rank descriptor as shown in the log of singular values. This ensures that all dimensions are fully utilized, avoiding collapse and improving representation diversity. The right side graph visualizes the difference in similarity between positive and nearest negative samples with and without hard negative loss. We observe that descriptors trained with hard negative loss show large similar differences, especially in higher dimensions. Next, I will move on to the effect of hard negative loss on uniformity. An uniform distribution of descriptors represents semantically similar images far apart while placing copies of the same image close together. Both Sino and SSCD are used as teacher models. However, only SSCD uses entropy regulator to achieve uniform distribution. In Figure 1, we clarify the significance of hard negative loss by visualizing features from different model configurations and obtain two findings. First, applying hard negative loss to final feature used as a descriptor results in a more uniform distribution. Finding 2, when using RSD, the uniformity of the teacher's embedding is transferred to student's embedding. Consequently, if the teacher's embedding already has a uniform distribution, applying hard negative loss to the final feature may yield limited additional uniformity. And lastly, I'll talk about the practicality. Our RDCD incurs higher computational costs during training, but shows significant efficiency during evaluation. As shown in the table, RDCD achieves superior efficiency across all metrics compared to previous methods. To conclude, we discussed three key aspects in our study and draw the following conclusions. RDCD utilized compact descriptors for ICD in a self-supervised manner. Combining RSD with hard negative loss effectively prevents dimensional collapse in lightweight architectures. It achieves competitive performance across various benchmarks and offers significant advantage in search speed and scalability for multimedia application. Thank you.